And that's not the right presentation. I know it looks good.
Oh my gosh, we're in chemistry now.
We are starting chemistry now. But first I want to go over the test just a little bit. So first, how to read the back side of this first page that tells you about your score. So you have numbers at the top. What I wrote in pen is how many points you got on the exam. So the first number is the number you got on the multiple choice. The second two numbers are for your remembering what the scientific method was, and then your application, and then of course equals total. I graded it out of a total of 50. There were 58 points. Yeah, I think I graded out 50 or 58 possible. Might have been 54. I have to go back and check again because I didn't check right now. And I think this is Jessica's. So here's Alex's. Okay. Then if you go down below, you have test items, and it has them separated by 1 through 5, 6 through 10, and so on. And then it has the test key. So that line is the correct answer for each question. And then underneath you have answers. If there is a letter in the answer, that means you answered that instead of the correct answer. If there's a dash, it means you answered the correct answer. And there were none that were blanks, so you don't have any. There are no blanks or double answers, so you don't have any issues with that.
Yay.
Okay, so I want to go over.
Can you keep this?
Yeah, it's also already uploaded on Moodle.
Oh, great, yeah.
I want to go over the 3 worst problems here from the test, just to review them. I'm not going to have you answer these because they were problems.
Can you say what numbers they were?
So
we can see if we got them wrong, right?
You all got them wrong.
Oh, everybody got them wrong.
Yes.
Okay, I got it. Okay.
So, which is why I'm not, there's not a lot of point in having you answer them again when you all answered wrong the first time.
I didn't know what to say.
Okay, electrically polarized, that was when we had the charge distribution switch. Remember we had the picture that had the negative charges with their center here and the positive charges
I do not remember that at all.
shifted. It was actually in baby blue with their center over here, and that was electrically polarized.
I don't remember.
And that was how we were able to stick the balloons to the wall, because you rubbed it on your hair to get it charged up. And then you put it on the wall, and it caused the charge to become polarized. It induced a charge polarization so that the opposite charge was close. The same charge was far, and because the force is stronger for closer things, it had a net attractive force. So the correct answer here was the charges have been rearranged so there's no longer a symmetric charge distribution.
Hello, Jessica.
Okay, so this is important in chemistry, right? A lot of the things we've learned here, I've kind of focused on the things in physics we're going to need for chemistry when we start skipping chapters. I made sure I got the things we need for chemistry and for earth science. And so this is an important thing for chemistry. Any questions about what electrically polarized means at this point? Now, when we get to it again, you probably will have a question then, but I want you to learn it, and then when we reiterate, when we go over it again, it'll come quicker. Next one that everyone missed, buoyant force acts upward on a submerged object because. This was the whole point of our lab this last week, was the buoyant force. And it was because when you have a fluid and something in a fluid, you had the force of the water pressure, in our case, since it was water, that was pushing down on the top, and the force of water pressure on the bottom that was pushing up. And because pressure increases with depth, this down here had a higher pressure, so a higher force. So the pressure against the bottom is greater than the pressure against the top, which is why you had a net upward force giving you buoyancy.
Did we got this one wrong too?
Yeah.
Okay.
That's why I didn't grade it out of the full, I figured if everyone got them wrong, something terribly, terribly went wrong, right?
If everyone got it wrong, we should throw it out.
What I said.
Oh, I know.
Okay.
I just said it. And
Okay, just making sure. Okay, the last one. And I went over this in our review lecture even. The acceleration of a vertically thrown ball at the top of its path. If I throw it straight up at the top of its path, what's the acceleration?
Zero.
No, its velocity there is 0.
Oh.
It's 10 meters per second squared. Because if its acceleration was 0, it wouldn't change velocity. It would just stay at 0 velocity and would hover.
You done tricked me.
I went
Certainly
around that
didn't
one.
mean
You
to.
did, yeah, you're fine.
So during the entire thing, the acceleration was the acceleration due to gravity.
Wait, you're throwing out these questions?
Yeah, I think I threw out 4 total.
Thank you very much. I appreciate that. Does that make our grade go up?
Yeah, I think it's actually I will just
Did you already put it in the Moodle?
yeah, I put it in the Moodle on Friday. I told you.
Oh, yeah, the test grade.
I told you I would have it. I didn't tell you after it was done, but I told you I
That
would.
could become better is what I'm asking.
Um,
I think or that's already included.
it's well, what you have there is the raw score, and then I have it recorded in the grade book out of, and I'm going to check where I have it recorded out of in the grade book right now. Yeah, I recorded it out of 50. So I actually threw out 8 questions. No, I thought that was pretty excessive already.
So, again, my question is, the grade that's recorded in the grade book
Yeah.
includes those 8 that you threw out?
Yes. Yeah. So you have the number that's on there out of 50 is what's recorded in the grade book. Yeah. Instead of out of 58, because that's how many points were on the test was 58.
Okay. I get what you're saying. I'm following now. Okay.
Okay, most of you did really well on the scientific method portion. If you missed some points, look over it to figure out why you missed points, because it's going to come back on the final exam. No point in missing that again on the final exam if you missed it now.
Are all of these coming back on the final?
The only one you know is coming back is that one.
That we
And others may or may not.
That's comforting.
Okay, chemistry. I've been saying ubiquitous,
Science.
but no, it's
You're saying
central science is what the textbook calls it. Chemistry is study of matter and the transformations it can undergo. He calls it central because it's very ubiquitous in our lives.
Oh, ubiquitous.
It's a good word.
Yeah, I don't know what it means.
It means everywhere.
Oh.
When I was in college, people were still citing Elvis everywhere. Elvis was seen checking food in the market, and so we called, Elvis was ubiquitous. Anyway, so I think I've mentioned, there is a certain segment of the population that talks about the dangers of eating chemicals. And there's like the food babe or something like that who says, if you can't read the name of the thing, you shouldn't be putting it in your mouth. Well, there's a lot of things that you probably can't read the name of. Like, I don't know, acetylsalicylic acid.
Acetylsalicylic acid.
Pretty close. Acetylsalicylic acid. We put it in our mouths a lot because acetylsalicylic acid,
No.
Is that Advil?
it is actually, it's aspirin, whichever is
Aspirin.
Advil's aspirin.
Oh, is that the abbreviation for aspirin? Acetylsalicylic acid?
Teaching. Go be a nurse. Oh, no.
So just because you can't pronounce it doesn't make it bad. Now, water, we can all pronounce dihydrogen monoxide, so I suppose that it's okay to eat water, but it's a chemical too. I say eat, of course, we drink water generally. So here's a picture just to illustrate chemistry. And this just has us pointing out some things that are chemicals in this picture. So what stands out to you as a chemical in this picture?
Oh, water.
Okay, water. There's, I think this here is a bottle of water, so let's say that's water.
Water. That looks like olive oil, but
Okay, then we'll just go to the sink and say what comes out of the sink.
exactly, that's what I was thinking.
Well, there's things that are made out of metal in there.
Okay.
Plastic is, wait, what are we saying again?
Okay, so I'm going to point to the one that it's going to on the next slide show. I'm just going to call this a plastic. The countertop is a plastic, just like your desktop's a plastic.
The vegetables.
Okay.
Chemicals.
The soil in that plant.
Vegetables and fruit, because we know that tomatoes are fruit. The what?
The soil.
The soil, okay.
Are we wanting all natural?
Actually,
chemicals, or-
I don't think there's soil in this picture. We're talking about all chemicals.
Well, glass is made out of chemicals.
Okay, glass. So once again, I'm going to.
The soil in the plant by the sink.
Oh, is there? Okay, I was just looking in the wrong place. Ah, yes, there we go.
Yeah, I'll be Vanessa.
Okay, so you get the idea. It's everywhere. Here is what they have, and they have words that are more complicated than ours. Transparent matrix of processed silicon dioxide.
That last one, you wanna say that one?
Which one?
That
This one?
No, other side.
This here?
Yeah.
Chlorofluorocarbon-free refrigeration fluids.
That was a 10 this week.
Wow. That one's 1600.
The chlorofluorocarbons are known to cause a breakdown of ozone in the atmosphere.
What is
Yeah.
it?
The chlorofluorocarbons,
Chlorocarbon? I got it.
like dichloro-difluoromethane is.
All right.
That's bad for the environment, or bad for the atmosphere. And so that's why it says free.
Free. Okay.
So notice transparent matrix of processed silicon dioxide, more commonly known as glass. Glass, sand, or silicon dioxide. Chemically disinfected drinking water. Okay, so I did and ultimately point to the right place for where they selected it. Chemically disinfected, yeah. Because we kind of want it to be safe.
Yeah, we put fluoride in all of our water.
Caffeine solution. Nobody picked on the coffee.
Oh shoot, you right.
The
Radiation,
microwave.
right?
That's a type of radiation, just like light is a type of radiation. That doesn't fit into chemistry. That fits into physics, though. Thermoset polymer, the cabinet tops. Thermoset means you heat it up and you cast it and then you cool it. And so that's a plastic polymer. The prescription medicine stored in the refrigerator. Already talked about the refrigerator. Electric energy came from either burning fossil fuels or possibly nuclear power plants. Those are two examples of chemical reactions. The metal you already pointed out. Roasting carbohydrates, fats, and proteins in the oven. Fertilizer-grown vegetables. They got the soil, I guess, there with the vegetables. And they pointed to the natural gas with an odoriferous sulfur compound. Natural gas you can't smell. And since you can't smell it, if you had a natural gas leak and they didn't put that odoriferous sulfur-containing compound in there, you wouldn't know there's a gas leak until you had an explosion. So that's why they put something in there. So, well, yeah, there's that. Okay, so in chemistry, we're going to be looking at a submicroscopic world. Tiny, tiny things. So 1 grain of sand has 125 million trillion. Anybody know what the word for million trillion is?
Million trillion.
Wait, what you mean?
Billion.
What's the word?
Okay, after million comes billion.
Then
So
trillion.
1,000 million would be a billion. And then a million would be a trillion. And so a million trillion would be what comes after a trillion.
Is it quadrillion?
Yes, it's quadrillion. So how big is that number? How big is this number? Well, roughly 250,000 sand dunes of this size would have 125 million trillion grains of sand. and each grain of sand has that many atoms. So we're talking about really tiny things when we're talking about chemistry. Going through some history of the atom. So we're basically now starting to talk about atoms, the things that stuff is made up of. In 465 BC, that means 465 years before the birth of Christ, Democritus, from whom I believe we have democracy, decide that if you take something like, let's say, a piece of paper and you tear it in half, you have two smaller pieces. Then if you take one of those, you tear it in half, you'd have two even smaller pieces. And if you kept going, he theorized, he hypothesized that eventually you would get to the smallest little piece that could not be torn apart. And so he said that smallest piece must be indivisible, so he used the Greek word for indivisible, atom, to describe that smallest piece. So Democritus, many hundreds of years before the birth of Christ, said that everything must be made of these smallest pieces. And he had some other things here. All matter consists of these pieces. They're just indestructible. You can't destroy the atoms. We will learn many of these things are untrue. You can destroy atoms, it turns out. You can, I say destroy. When you have a nuclear reaction, you change the atom. It's not truly destroyed, it's changed. Atoms are solid but invisible. Why would they be invisible?
I feel like that's a way of saying you can't actually see it because it's so small, but they don't have a word for it.
Exactly right. That is exactly right. Atoms are homogeneous. Well, we'll learn about that later. They different size, shape, mass, position, arrangement. They're small. He believed these are absolutely untrue. Democritus believed that solids are small, pointy atoms, and liquids are large, round atoms. You hypothesize. It doesn't mean it's correct. It's the idea you came up with based on other scientific ideas. And his scientific idea was the solids being small and pointy atoms, they're going to stick together and not slide against each other, whereas the liquids being large, round atoms, they can roll around each other and move so they can flow. Well, moving forward, we come to Aristotle. About 100 years later, still 335 years before the birth of Christ, he didn't believe in the atomic theory. He didn't think Democritus was right. He believed that everything was made of four elements, and once again, we know this to be untrue. Those four elements being earth, which we've already learned. He said it has a natural position of being down. And then water, natural position being on top of the earth. And air, natural position being on top of water. And fire, natural position being on top of everything. He actually had a fifth element, right? These are four elements. So there's a fifth element. You might have heard that word. Well, that wasn't supposed to happen. There's also a quintessence. A fifth element, and that's the perfect stuff that's not part of this earth. So the quintessence would be what the moon's made out of, for instance. And so he thought that everything, you take my 5 kilogram mass here, this is made out of a whole lot of earth because it wants to go down. Not much fire, doesn't want to go up. He thought everything was just a combination of those. Quintessence, the fifth essence. So people largely abandoned the ideas of Democritus and adopted Aristotle's because, well, you've probably learned a little bit about logic, and there's a lot of fallacies like, ad populus, everyone believes it, so it must be true. Or an appeal to authority, Aristotle is such a great thinker, he must be correct. And so people abandon the idea of Democritus to follow Aristotle's idea because, he's such a great thinker, he's so smart. You shouldn't go following after people just because they're so smart. You should still evaluate what they say.
Are you going to be quizzed on the quintessence?
On the quintessence? No.
Okay.
No. Okay, now we get to the, quote, modern era. So we're jumping well ahead. John Dalton explained why chemical reactions occur in certain ratios. So much of this reacts with so much of that to make this. And I invoked the idea of atoms again, going back to Democritus, and that there are different types of atoms. And now we have our first vocabulary word. This is definitely something you will be tested on. An element. And an element is a material made of only one type of atom. Now, if you look back there behind you, you have what we call the periodic table of the elements.
Yeah.
And so each one of those things is a type of atom, so you can have the element. You can have elemental hydrogen. That would be pure hydrogen. Or you can have elemental boron.
Are we gonna have a test on the element? Like on the whole periodic?
No, I have it coming up in a slide. I'm not going to jump forward 3 slides to show you where it says no. But
Okay.
that's
If you're teaching about the periodic table, there is a song.
there
You know
is.
the song?
I don't want to sing it, but yes.
Wow, I don't know the song.
I know the song. I know the entire periodic table on a song.
There
Wow, that's pretty impressive.
I know things.
I do not. Okay, so an element is a material that's made of only one type of atom. If you have elemental gold, well, that's really good, right? Because that's worth a lot because it's pure gold. None of that, white gold or something like that. It's pure gold. Okay, now we move forward. Now that was 1888, I believe. You can check 1880. Now in 1904, we have J.J. Thomson. The textbook, I think, only credits J.J. Thomson here. J.J. Thomson discovered that you have these things he called cathode rays coming out of material. And with careful evaluation, he determined that it had a negative charge. And then Robert Millikan, a year or 2 later, did an experiment, actually it was him with somebody else, where he measured the charge to mass ratio. And combining the information from those 2 researchers, we know the charge of an electron, which we already studied in our physics section, 1.602 times 10 to the minus 19 coulombs. But he determined that matter contains electrons. So the atoms that our tabletop is made of contain electrons.
Do they only have electrons?
Not only electrons. And so the idea that Thomson came up with, he called the plum pudding model, was that matter, like this tabletop, is made up of a collection of electrons, little positive charges, with a slurry of negative, excuse me, I said that backward. Electrons, little negative charges, with a slurry of positive charge everywhere. So now, plum pudding apparently is a food they eat in England. I like to talk the oatmeal and raisins model, because that makes more sense to me. The oatmeal is that positive slurry that's everywhere, and then the raisins are the little points of negative charge. That was J.J. Thomson's model. Unfortunately for J.J. Thomson, he was not correct.
Positive charge.
So see that picture, the whole red stuff is positive.
So does this positive charge have a name? So like the electrons would be negative.
The electrons are negative, the positive charge does not have a name, no.
Oh, they're just positive?
And remember, this is discredited. It's not the current theory, it's J.J. Thomson's theory. So why is it discredited? Well, the Rutherford gold foil film. Ernest Rutherford was a researcher in his lab. He had a newbie that was named Hans Geiger, who you might have heard of. You've heard of the Geiger counter, named after him. They were studying nuclear physics, which we'll get to. That's going to be our lab. Wow, might be this week. Not sure which week it is. But anyway, Rutherford gave Geiger an experiment. We said, let's take some gold. And gold is what we call malleable. The properties of elements is an important thing for us. Malleable things are things that if you hit it with a mallet, they will just squish. As compared to things that are brittle, if you hit them with a mallet, they fracture. So gold is malleable. You can hit it with a hammer and it just squishes and squishes. You can make it really thin, make what we call gold leaf. And so it's to make a really thin gold film, and then we're going to fire these little things that we call alpha particles, we'll learn about those, at the gold foil. And according to the plum pudding model, you're going to have this generally positive charge everywhere in the foil with little points of negative charge. And so when the alpha particles hit, they'll go through, but they'll probably be slowed down just a little bit by going through that positive slurry. And if they hit the electron, they might deviate just a little bit instead of going straight. But what they found was most of them went through without slowing down at all. If it goes through without slowing down at all, didn't hit anything. So most of the atoms must be empty. It must be mostly empty space in that foil. But some of the little alpha particles bounce straight back. Just think about if you were to fire a bowling ball. Well, this is actually the description that Rutherford used. Imagine that you fire a cannonball at a piece of tissue paper. What's going to happen when the cannonball hits the tissue paper?
It's gonna go right through it.
It's going to go right through. Tissue paper is going to have a very minor effect on its speed, right? But if it hits that tissue paper and it bounces straight back off of that tissue paper, or it comes back to the cannon at a high speed. That's how shocked they were, because they thought that you would have just, going through this little slurry like the tissue paper and nothing to slow it down. The fact that it bounced back means it must have bounced off of something much more massive. You saw with the whole collision experiments, when you had a lighter car hitting a heavy car, it bounced back. So he had to change the model. So he came up with what he called a planetary model, where he said instead of having a generally positive slurry of charge with little electrons and points of negative charge, you have mostly empty space, since most of the particles went straight through without any interaction. But then you have a really massive central part that is positively charged. So he says, like the solar system with the sun, a really massive central part, and then mostly empty space with the planets orbiting about it. Now, this sounds more realistic. Most of you probably have enough general science from grade school and so on to have an idea saying, yeah, this sounds more realistic. But it's still not correct. And I point that out because when I was in high school, I graduated from high school thinking fundamentally this was correct.
That's very unfortunate.
Yes. So next we come to the Danish physicist Niels Bohr, who came to work with Rutherford. And they noticed right away that there were definitely flaws in Rutherford's planetary model. For class this level, we're not going to point out what the flaws are and why. But Niels Bohr suggested, okay, well, maybe there's only certain energies electrons can have, and so they have what he called steady state orbits, where the electrons can only have this energy or this energy. And according to him, they were going around in circles. And so the Bohr model, we have what we call quantized energies for the electrons, only certain energies. In class, either Wednesday or Friday, I'll be doing a demonstration that shows the validity of that assumption. And so he still has the nucleus at the center, but then he has the electrons in different energy levels orbiting about it. Now, the nucleus we've already talked about, it has protons and neutrons in the nucleus. It's positively charged. Initially, they thought it was just protons, just positive charges. But they soon learned that the mass of the nucleus did not scale with the number of positive charges. That is, you go to an atom that has twice as many positive charges, but the mass is like 3 times bigger instead of 2 times bigger. And so they said there must be something else in there that's adding to the mass. And that's how they came up with the idea of neutrons. But this is still not correct. It's still not correct because in trying to locate the electrons, scientists quickly discovered we have no idea what paths the electrons are going in. The idea that they're going in circles, that doesn't make sense. They're doing some kind of crazy path, and we can only calculate where they're likely to be. So the quantum model, the current model, so this is the model we currently believe to be correct. Now, don't be confused. They thought this was correct. Before that, they thought this was correct. Before that, they thought the Thomson one was correct. They thought these were correct all along. Science, the scientific method, you come up with, you observe something interesting, like, matter is made out of whatever these things are. And then you hypothesize about them. And so the first hypothesis, it made predictions, and Rutherford tested the prediction and broke it. And so if the prediction doesn't work, then you go back and you modify the hypothesis because you have new information. And then because of other experimental variations, Bohr came up with a new model because it broke the Rutherford model. But then there were problems with Bohr's model, and so we have this quantum model. Now, in terms of time, all of this was completed from 1880 to about 1915 or 1920. So it was a pretty short amount of time when you think about it. 40 years, people were working on atoms throughout the entire process of going from the ideas of Aristotle to today's quantum model. In the quantum model, we still have a nucleus that's made up of protons and neutrons, and we have an electron cloud. We don't know where the electrons are, but we know they're in this cloud. And the shape of that cloud can vary. So here's another example of the electron cloud, but it's very complicated. And this is not spherically symmetric at all. So the electrons aren't necessarily in a spherical shell. They're not doing circles for sure. And all we can do is calculate where they're likely to be found. And so everywhere where you see something in color here, that's where you're likely to find electrons for this specific atom. And we have 4 variables we need to describe the model. So it's pretty complicated. Now, are you going to have to know all the ins and outs of the quantum model? Absolutely not. But it's important to know that the scientific method has led through a progression and know about what those steps were along the way. Okay, first of our woo clap questions.
Wow.
Are we doing it on our phone?
Yeah. And I will write here again, www.wooclap.com. That's the URL. We only have 2 people in yet, so okay, you can start answering now, but I'll give you extra time because people still need to get connected up. Which of the following are incorrect statements about the atom? All right, 4 of you are already in. That's good.
Incorrect.
And this is one where you have multiple answers.
Oh, this is a multiple answer one?
Yeah.
Well, dang.
Well, hopefully we've got at least one of them, right?
Okay, everyone's answered. Excellent. And
Yes.
we had 1, 3, 1, 3. Now this was primarily checking your preconceived ideas. I have ruled out one, but only one of these.
You said there's multiple, correct?
Yes.
Okay.
So I've ruled out one of these. Which one did I rule out?
Are perpetually moving.
We know that they actually are mostly empty space. That's true.
Guess I'm the wrong one.
Oh, I put that one.
Oh boy.
Okay? Have been around since the beginning of the universe.
Yes.
Yes.
No.
Well, we have yes and we have a no from
Blank
Annabelle.
faces.
She's totally right on one of those 2.
I would say
Love that.
yes, because maybe we didn't know that they were there, but how else would organisms have?
Existed.
Yeah.
I'll give you 2 answers.
Yes
One,
or no?
One, a creationist answer that says that the earth was created at the same time that life was created.
Right.
If the earth was created at the same time life was created, since everything's made out of atoms, then they were in existence from the beginning. Then there's the scientific answer, which says that it all started with the Big Bang, And if it all started with the Big Bang, it turns out that in the earliest moments of that Big Bang,
Would have been when they were.
there was way too much energy to have atoms. In fact, it wasn't until around 300,000 years after the Big Bang when you could have the first atom, the first neutral atom with electrons and protons at the core.
So are we going
So-
with the creationist view in your class?
Well, in my class, I want you to actually understand both sides. I want you to know the scientific argument. I don't want you to say, oh, no, the science is wrong. I want you to know science says this. Why does science say that? Because science is trying to come up with an explanation that doesn't involve a miracle. And that's the best answer we can have without a miracle. Okay, now the other ones, so the top one, atoms have been around since the beginning of the universe. You could have answered either way, and I would have said that's fine depending on your worldview. Alex?
Are we gonna get tested on that question? And if you,
I'm not going to test you on one that has you answer right or wrong if the answer could be different based on your worldview. I would say based on the scientific view, what is,
yeah, that's
or something like that. So you know, this is the one I'm supposed to answer.
I was just making sure.
Yeah. I don't think it's fair to just say, oh, yes, and you must believe the way I believe.
I was more worried, like, which one will we choose then if that did come?
Yeah, I don't want ambiguity on the test. Okay, so this one could have been either way. Atoms are perpetually moving. It turns out that that is a fact. Well, we were looking for the incorrect ones. So this is also true. So that wasn't a correct answer. Atoms are manufactured in plants and in humans during pregnancy. That one, my friends, as you can tell by me laughing, that was a correct answer. This is false.
The fact that it's correct, but it's false.
It could be incorrect. All right, so atoms are not created in plants and in humans during pregnancy. What's being created in humans during pregnancy?
A baby.
A baby. And what's that baby made out of? Well, that's not physical science, that's biological science. But it's creating cells out of atoms. The atoms aren't being created. They're being used to build things. All right. So the elements. I had to update this. If you look in your textbook, the numbers will be different because the textbook is a few years old. So if you turn around and look at the periodic table is also a few years old. So our periodic table, if you look here, element 113, UUT, that's I think tritium, or something like that. It's 113 elements is what it means.
Like one of those we don't know if it actually exists.
No, these have all been verified now. So this is old, and so it has the star there, still to be discovered. It's been discovered, it's been named. And I have it on an upcoming slide. Likewise, Pentium, Septium, Octium. They all have names now, like Nihonium or Japan. So how many elements are on this periodic table? A total of 118.
I was gonna say that.
Something that can confuse is these bottom two rows. These bottom two rows are not separate. Because of space, these things here are where these rows go. So this entire row should be right here. This entire row should be right here. It's just space saving so we don't have a really wide chart.
Are those rows like all really similar properties?
They are similar properties, yeah. Now, in terms of naturally occurring elements, everything except for 3 up to, where's 91?
Huh?
I said, where's 91?
Just down there.
Up to here, 92. All of these are generally found in nature, except for there's only trace amounts, and you actually come up all the way up to California. There's only trace amounts of neptunium, plutonium, americium, curium, berkelium, and californium.
Is that why they're white?
That's why they're white, yes. Well, actually, that's not, these are man-made, that's why they're white, actually. The ones that are white are man-made. They're
Okay.
not generally found in nature, but you do find up to California in nature trace amounts. They were thought until recently not to be found in nature at all.
Okay.
And so, other ones that are not in white, francium was thought to not be found in nature, but they found it in trace amounts. Technetium was thought to not be found in nature, but they found trace amounts. You see, technetium is still right here, saying it's only man-made. And this one here, oh man, it's like astatite or something like that, was thought to be not found in nature, but now they found very trace amounts.
Call it an unicorn.
I could. That's actually a good idea.
You don't need that.
Well, I still do because of these.
Question,
Yeah.
why are they red?
Why are they red? Okay,
Those
so
guys are those like the gases ones?
those are, well, these here are the noble gases, but
Yeah.
these are not.
Exactly.
So- I'm not 100% sure on why those are red. There's nothing here. To say why.
Stable.
Okay, so any material consists of only one type of atom element, but we can have materials made up of multiple kinds of atoms, and those are compounds.
Compounds.
So, protons are in the nucleus. They carry a positive charge. You've already learned that. They're about 1,800 times as massive as an electron. So when we talk about the mass of an atom, the mass is almost exclusively in the protons plus the neutrons. Neutrons have effectively the same mass as the protons, very slightly different, but no charge. So the mass is the protons plus the neutrons. If an atom is neutral, which is the standard state for an atom, as we learned in electricity, that means it must have the same amount of positive as it has negative.
Neutral.
To be neutral, it has to have as much positive as
Okay,
negative.
so it's positive.
No, it's neutral because it has to have the same amount of positive as
You
negative.
just said neutral. Keep going.
Okay, so if you have something that has one proton in the nucleus, how many electrons should it have?
One.
One. That's 5 protons in the nucleus and 3 neutrons. How many electrons should it have?
2. 5.
5, because it needs to have the same number as it has protons to be neutral. All electrons are identical. You can't tell one electron from another. Likewise, you can't tell one proton from another or one neutron from another. They're all identical. They all behave the same. And the fact that electrons repel other electrons is why atoms can't clump down and just shrink to nothing.
I don't think I did any class. Can you go down for like 1 second?
I can go back for 1, 2, 3.
This internet here, that's not.
Really?
Yeah, my computer goes on and then it goes off. When it goes on.
The Wi-Fi?
Yeah.
I will contact them.
All right, I'm good.
Okay, atomic number, a new vocabulary word. The atomic number is effectively how many protons are in the nucleus. It has the symbol capital Z, and if you look here at the periodic table, the number in the top right-hand corner is the atomic number. So hydrogen has atomic number 1, helium 2. What's the atomic number of titanium?
22.
22. What does that mean? There are
22.
22 protons in the nucleus. What about neutrons?
Can I use a checker?
Also 22?
One.
It's actually not also 22. It seems like it probably should be, but it's not. It turns out that as you get bigger and bigger atoms, the number of neutrons increases faster than the protons does.
So,
So-
would you double it?
No.
Oh, okay.
So you have down here the mass. 47.867. We'll see another slide.
You
like
have
this
to
when it's on.
calculate it, don't you?
Well, it's not a hard calculation.
I know, but it's still a calculation.
If you have 47.867, just round that off. What do you round 47.867 to?
I said that, Mr.
48.
I am right.
This here is the atomic mass number. The atomic mass number is 48. The atomic mass is 47.867. And that atomic mass number, which has the symbol A, is the protons plus the neutrons. So if A is protons plus neutrons,
You do the atomic mass number minus the protons.
that's right. The atomic mass number minus the atomic number gives you the number of neutrons, which you see down there at the bottom.
Oh wait,
This is a new slide.
can you go back for 2 seconds?
I also need this.
You're gonna post these, right?
Yeah.
Oh, no.
You know when you're gonna post these? Because I need to break all of my notes.
I will try to post them this afternoon.
Okay.
Okay, so things that are in the nucleus are called nucleons. So nucleon is a generic term for things in the nucleus. Things in the nucleus, protons and neutrons. It's an exclusive list, nothing else. Isotopes, you probably heard of the term isotope. Like if you watch The Simpsons, their baseball team is the Isotopes, or Topes for short. Isotopes are atoms that have the same number of protons, that is the same atomic number, but a different number of neutrons. So you can have, for instance, hydrogen. Hydrogen has 1 proton and 0 neutrons. Or you can have an isotope of hydrogen that we call deuterium that has 1 proton and 1 neutron. It's still hydrogen because hydrogen means 1 proton. The element name goes with the atomic number. And then you have a hydrogen atom that we call tritium that has a proton and 2 neutrons. Still hydrogen because it has 1 proton. How many electrons should you have if you have tritium? 1, because it's just balancing the protons, not the neutrons. And that's the reason we name the elements by the protons. The electrons are what really tell us about the properties of the atom. And so if it has the same number of protons, it has the same electronic structure, same properties. Atomic mass, I've already talked about the atomic mass number. The atomic mass is measured in special units. They're called atomic mass units, with 1 atomic mass unit being 1.661 times 10 to the minus 24 grams. So if I take that atomic mass that's shown for titanium, 47.867, and I multiply it by 1.661 times 10 to the minus 24 grams per atomic mass unit, that will tell me the actual mass in grams of the nucleus of a titanium atom. Well, of a titanium atom, because the electrons are so small in mass compared to everything else. All right, we are almost done with today. Our second clicker question. The atomic number of an element matches the number of, and answer all of the answers that are correct again.
Number is B. What an element matches the number.
Okay, oh no.
I have it because
Yeah, only 4 people have answered, yeah. Yes, Alex.
Request that you upload this notes directly after class, because I don't have time to go over this again tonight, and I need to do it.
I have a class directly after class. I have to wait an hour.
Okay.
Okay, everyone's answered now. We had 3 that said number 1, 1 that said number 2, 4 that said, well, C, and 0 that said none of the above.
Oh, it's A and B. I didn't read B.
Okay, she is correct.
Good job.
Z means the number of protons. That's what it means. But if it's neutral, then the number of electrons is equal to the number of protons.
Tricky.
So those 2 were correct. 4 people said proton plus neutrons in the nucleus. That's a different thing. What do we call the protons plus neutrons?
Mass.
Yes, that's the atomic mass number.
I almost said that, but I knew that it was
But you knew.
tricky.
Okay, here is the slide that Josie was looking forward to. The periodic table is a listing of all of the known elements. All 116 of them. Oh, excuse me, 118 of them. Very good, very good. All 118 of them. You do not need to memorize this.
Thank you.
Wait, do we get extra credit if we know a lot of them?
No, but what you will have to do is to be able to determine properties from the periodic table. So next class period, we'll start in on some of the properties that you can determine from the periodic table.
Denseness.
Density is not
Oh, I was talking about their,
the size.
properties, I'm sorry. I was on a different kind of property.
Oh, being in a relationship and all that right sometimes.
Yeah, that's.
Are you okay, Josie?
Oh, yeah, I'm just being honest, like, it's not always